Let's see a few examples of diagonalization. In the previous lecture, we have seen that an n by n matrix A is diagonalizable if and only if there exists a basis Vi of Rn such that the action of A on this Vi by left multiplication is just increasing or decreasing the length of each Vi's by a certain coefficient lambda I depending on the Vi. From a homomorphism standpoint, A is diagonalizable if and only if there exist basis vectors Vi on which A acts by sending them to multiples, as we have just seen. By this remark, it is clear that a rotation R alpha in R squared by an angle alpha which is not multiple of pi will have an associated matrix. See lecture 9.4 for associated matrix to a homomorphism, a choice of basis, which usually is denoted by A, and then here the homomorphism we are finding the associated matrix of, and here the choice of basis, the domain and codomain. So A, R alpha, Wj and Wi is non-diagonalizable for any choice of basis Wi of Rn. So here we are taking the same basis for domain and codomain. Why is that so? Because a rotation in R squared acts on any basis, just rotating in each individual vector by alpha. And therefore these vectors are not being sent to multiple one of each other. Except, of course, if the rotation is an angle pi, in which case the basis vectors are sent to their opposite. Therefore, here we are multiplying Vi's by -1 in this case. But if we exclude that case, the case of rotation of angle pi, any other rotation will be sending a vector to another vector which does not lie on the same line, and therefore this is not going to be possible. We consider now a more general example on which we would like to apply the procedure of lecture 1.11.2, which is the previous lecture to this one. Notice that the characteristic polynomial has degree n if A is an n by n matrix. Hence, establishing diagonalizability of a generic 3 by 3 matrix is already difficult because it requires to find roots of a degree 3 polynomial. And for a 5 by 5 matrices and larger, there is no general algorithm that can be applied for finding eigenvalues. It is a famous result in mathematics that there is no general formula that applies to any polynomial of degree 5 and above that involves the coefficients of the polynomials and gives as a result the roots of this polynomial. Okay, so making exercises for the students in finding, establishing whether a matrix is diagonalizable or not is kind of difficult because usually students do not know the formula to find roots of a degree 3 polynomial. Okay, so somehow one of the roots should appear obvious in the polynomial, and then one may divide by x minus that root and factor out the degree 3 polynomial as a product of x minus the root times a degree 2 polynomial, which can be easily factored in. Let's see a specific example of this. Determine if the matrix A is diagonalizable. First of all, notice that the matrix A has order 3, therefore its characteristic polynomial will have degree 3 as well. We will use the fundamental theorem of lecture 11.2. And first, we have to compute the eigenvectors of A. The characteristic polynomial PA of x is defined to be the determinant of the symbolic matrix A minus x times the identity matrix, which is the determinant of this matrix 1 minus x 1 0, because this is a scalar matrix with zeros everywhere except along the diagonal, whose scalars, let's say, whose symbols are just x's in each place. Therefore, this matrix can be obtained by this, just subtracting minus x on each entry in the main diagonal. The same matrix as in A, except that we subtract x on the elements in the diagonal. Now we have to expand this polynomial, and we see that there is the third column. It starts with 0 and 0. So there are two zeros. Therefore, it's convenient to expand the determinant along with the Laplace formula along the last column. So we get 2 minus x, because it is plus 1 minus 1 plus minus plus. So it is plus 2 minus x that multiplies the determinant of this submatrix, which is 1 minus x squared minus 1 times 1, that is minus 1. Now if we expand this, we will be getting 2 minus x times a degree 2 polynomial. Therefore, so altogether is a degree 3 polynomial, but we already have a factor, a linear factor, which is 2 minus x. And, well, finding the roots of the degree 2 polynomial is easy. And eventually we get this factorization. So we have 2 minus x times 2 minus x times negative x. This means that its roots are 2 and 0, but 2 has algebraic multiplicity 2, because it is 2 minus x squared. Therefore 2 is algebraic multiplicity, and the root 0, which corresponds to this factor, has multiplicity 1. MA of 2 is 2 and MA of 0 is 1. In order to see whether the matrix is diagonalizable or not, the theorem says that since the roots are real numbers, 2 and 0, we just have to check whether the geometrical multiplicities of the eigenvalues are the same as the algebraic multiplicities. Here we have the eigenvalue 0, and as I noticed before, if the algebraic multiplicity of an eigenvalue is 1, we don't have to check whether the geometrical multiplicity is 1, because this is automatically verified. We have that the geometrical multiplicity is always less or equal than the algebraic multiplicity, but it is always greater or equal than 1. Therefore, if MA is 1, necessarily MG must be 1. The only thing we have to check is the geometrical multiplicity of 2, which could be, since this is 2, this could be equal to 2. In that case, the matrix A is diagonalizable because there are no other eigenvalues I have to check. Or else, if the geometrical multiplicity is 1, then the matrix will not be diagonalizable. By definition, the geometrical multiplicity of an eigenvalue is the dimension of the eigenspace associated to the eigenvalue. And again, by definition, the eigenspace associated to an eigenvalue is the kernel of the left multiplication by the matrix A minus lambda I, where I is the identity matrix, A is our matrix we are starting from, and lambda is the eigenvalue we are considering, in this case 2. We get the following matrix right here if we just plug in the formula and the definition of eigenspace. Therefore, the geometrical multiplicity is the dimension of the kernel of this matrix, meaning multiplication on the left by this matrix. But by the Grassmann theorem, the kernel of left multiplication by this matrix equals the dimension of the domain, which is 3, minus the dimension of the image of left multiplication by this matrix, which is the rank of the matrix. Okay, so we have that this number here is 3 minus the rank of this matrix. What's the rank of this matrix? Well, we have to write explicitly down the numbers, the coefficients of the matrix. So we have negative 1, 0, 0, 0, negative 1, 0, and 0, 1, 0. The rank of this matrix is 2. The first two rows are linearly independent, and the third is a multiple of the second. Of course, the rank of this matrix is always going to be not maximal, because the kernel is never trivial. Since this is an eigenvalue, the kernel of this matrix cannot be just 0, by definition of being an eigenvalue. It will have a non-zero eigenvector associated, that is. And therefore, this rank cannot be maximal. And in this case, it could have been 2 or could have been 1. If the rank of the matrix were 1, then the matrix would have been diagonalizable, because 3 minus 1 would be 2, and that would be the geometrical multiplicity. But in this case, we see that the rank of the matrix is 2, therefore the geometrical multiplicity of the eigenvalue 2 is 1. Therefore, it is not diagonalizable.